My name is Piotr Zioło, and I represent Aura AI. And today I would like to present the algorithms that we develop at Aura AI to solve, to address, to deal with the problem of bidding in Google Ads. So this is the main problem that we work on. It's the bidding on the platform with Google Ads. So the second message I would like to convey during this presentation is about a certain family of methods of algorithms that is not that well known in machine learning community. You might know that there are many tribes in machine learning community. There are people who are more into deep learning, neural networks. There are other which mostly use ordinary machine learning, SVMs, linear regression, and this kind of stuff. Then we have a tribe concentrated on genetic algorithms. Then we have Bayesians, and then we have people mostly concentrated on algorithms based on logic. And these communities not always communicate well. They do not often know what the other community is doing. And even within those communities, there are subdivisions. So today I will present methods that were developed by Professor Warren Powell from Princeton University and Peter Frazier. And so because Professor Powell mostly works in operations research, and he is famous in the area of logistics, and he also had huge successes in this area because he earned like millions of dollars for American trucking companies with those algorithms, but he is not so well known outside of this community. So for instance, if you take the book by Sutton and Bartow, Reinforcement Learning, which is the go-to book for reinforcement learning, you will see that Professor Warren Powell is actually mentioned there, but only somewhere in the beginning. And this mention is like, if you want to see the perspective of operations research community, then see Professor Powell's book. So yeah, so these algorithms do not transfer between communities, and I would like to introduce you to this method of which is called knowledge gradient. And you will see that the ideas behind this method are pretty similar to what is used in other communities. And I would like to also convince you that it is a pretty useful method for adaptive learning, quick learning. Okay, so the presentation, first I will briefly introduce the company, then I will present the business problem that we are trying to solve, then I will go to a mathematical formulation of this problem, and I will present some possible solution that you could try to address this problem with, and then I will move to a problem of testing decision-making, sequential decision-making algorithms, which is obvious in the area of reinforcement learning, but not so much if you have like a real system, not an agent like in a game, but a real system where you have to deal with reality and interact with reality. How to test those algorithms is not that obvious. And then I will move to the algorithms themselves. And finally, I will provide some simulation results of the algorithms that we have tested. So, okay, so the company, actually in Poland, formally, we are Wizard Forms. The Aura AI is our brand name, but okay, that's just a detail. It was founded 3 years ago, and this is still a pretty small startup with less than 20 people, but it's gaining traction recently, and we get many new clients, as you can see at the bottom of this slide. And what we are doing, we are actually aiming to provide a comprehensive solution to automate Google Ads campaign management. But for now, our first product is a bidding engine. This is only for bidding on Google Ads. And okay, so the team that was working on the algorithms I will be presenting today, it's me and 3 other guys, Hubert Juskowiak, Jędrzej Kardach, and Michał Wojtal. But we also cooperate closely with people from Princeton University, from the Operations Research and Financial Engineering department. It's a pretty good department because this is the main source of quants for Wall Street, for instance. And they do stochastic optimization. And yeah, so we cooperate with Professor Warren Powell and his PhD students. And one of those PhD students is given here, it's Duncan Lee, but we also cooperate with other people from there. Okay, and as I mentioned, Warren Powell is the author of this method of knowledge gradient that I will be also talking about, will be one of the main focuses of this talk. Okay, the business problem. If you are not familiar with Google Ads, this is a platform for advertisers who want to show their ads in Google. So they want to define which queries which keywords, which phrases they are interested in showing the ads for. So, and moreover, beside defining the keywords, they have to also say how much they are willing to pay for a click in their ad. So whenever anybody searches anything in Google, like for instance flights to New York, then an auction is run behind the curtains within milliseconds by Google, and those bids are put into a Victory auction, which is a second price auction, and then the winning advertiser gets the first spot, and this is also indicated by this word ad in Google, and these results are above the organic results. So you have to pay to show there, and the highest bidder appears on the first position, but because this is a second price auction, the first bidder pays the second price, the bid of the second bidder, and so on, right? The second bidder pays the third price. So actually what you have to do when you do the bidding, and this is the problem we are solving automatically, you have to balance on one side the profit, the revenue that you expect to get from this traffic, from those clicks, minus the cost of all the clicks that you pay to Google. And this balance is not necessarily obvious because there are many factors that affect this environment. So this is a flowchart of the system, a simplified version. So we have the searches, we have the bid that our system produces, we have the bids of the competition, we have then the ad position processed by Google Ads, and then our ad is shown. So we have competing ads with their attractiveness, how appealing they are, and how relevant they are. Yep.
Do you also get the bids of the other people, like all the data, or only your own position?
The thing is that currently you don't even get your ad position, because it was until September that you got this position. Nowadays, you even don't get your position because Google blocked that, but you get if you appeared on the first position, and you get, I mean, how often you appeared on the first position and how often above the organic results. This is the only information you get. And of course, you don't get information about your competition, at least precise information. You can try to infer that. Okay. Then we have those competing ads, and then those people decide whether they click your ad. So you get a click-through rate, which is a proportion of clicks to all impressions, and then these people are redirected to your website, and then they decide if they want to make a purchase, make a booking, or just give you some money for the service that you provide or product you sell. And all of this is affected by environmental effects. So, for instance, what day of week it is, what day of hour of day it is, by different events, whether it's Christmas, Black Friday, it's affected by weather, it might be affected by many other factors. So it's a pretty complex system, and the typical goal is to maximize profit. So this is the revenue from all the conversions that you get on your website, minus the cost of all the clicks. And to show you how complex is this problem, you can see here a time series of the conversion rate in time for a group of keywords. So it's very, very noisy. And here you can see a trend of the click probability throughout time for a single, also a group of keywords. So the point here is that it's non-stationary, right? There are some seasonal effects, you might find it, but you have to be aware that there is non-stationarity, and your algorithm need to adapt to this changing reality and those different factors that affect your profits. Then you have the adversarial behaviors, and you can also affect your competition somehow, but we do not go into this direction too much because it's not competitive as, for instance, in algo trading, where these algorithms really fight with each other. So, but you have that. And there are also other goals. So many clients just want to maximize conversions, others just want to maximize clicks, others just want to maximize impressions, and so on and so on. So it adds to the complexity of the problem. Okay, so the mathematical problem definition. So don't be scared by this slide. I mean, there are, according to Professor Powell, a proper definition of a reinforcement learning problem consists of 5 elements. This is the state variable, the decision variable, exogenous information, and the transition function and the objective function. So in our case, the state variable is the physical state, which is the budget that we have, and we spend this budget throughout a day, and every day it refills. Then we have, for instance, the date, day of week, weather, events, etc., etc. Then we have all the information that was revealed throughout the entire run, I mean, throughout the entire history, but not all of this information might be known to the agent. So there is the time series of impressions, there is the time series of clicks, of conversions, and so on, and some of which you know because Google provides that information, and some of which you don't know. And then we have the knowledge of the agent, then we have the decision variable. So in our case, it's the bid. So we will here concentrate that you have a single bid for a single keyword, and this is what we will be covering in this presentation, but you can also think of it as a multi-dimensional problem. But okay, here it's simple. It's just the bid, the amount that you are willing to pay for a click. Then we have the exogenous information. So this is all the information that becomes available at time t. So again, this is the same as goes into information, but this is all the information throughout all the history, and this is what you get to know at time t. So for instance, this is number of searches, number of clicks, conversions, value per conversion, and cost per click. These are the most important factors. Then the transition function, it defines how the state changes according to the external conditions. Oh, sorry, I should put here action, of course, too, but here for Google Ads, you have so little impact on the actual state that it's rather reasonable to not include here. And the objective function is to maximize the expected profit over an infinite time horizon. So you have the discounted rewards, and the reward that you get is the number of conversions multiplied by the average value of a conversion minus the number of clicks times the cost per click. Okay, so that's the mathematical formulation. So, well, there are many methods in reinforcement learning, and many of those methods depend on your ability to capture the states and to capture the transition between the states and your impact on the states. So these are Monte Carlo tree search, Markov decision processes, or for instance, Q-learning. But because here we have so little impact on the state transitions, and we know only very fractional information about the states, these methods are not very useful. So what we chose instead are solutions for the multi-armed bandit problem. So if you don't know what multi-armed bandit problem is, you have let's say, 10 choices for 10 machines that you can play with. They have rewards, random rewards. You will try a machine and it might give you nothing, then it will finally give you some reward, but you don't know which machine will give you the best reward. Right, so you can imagine that their average rewards over time are like this, and you have to discover which machine is the best. So you pay for learning with lost time, And in other problems, you also pay because, for instance, in Google Ads, you have to pay for clicks, right? So if you test new beats, new machines, so then you just waste money. So the point here is to learn as fast as possible. So all those solutions to multi-armed bandit problem are aiming to learn as fast as possible with as little data with the data that you have. So different communities have different solutions to this problem. So for instance, computer science community, they have their upper confidence bounds, so this is a pretty engineering approach. Then the Bayesian community, they have Gaussian processes plus the expected improvement. And finally, the operations research, they have the knowledge gradient. And we will compare those in a couple of slides. Okay, you could also think if you are more into machine learning stuff and you do forecasting, you do modeling, you feed models to data, you can think, why not do it simpler? Because we have the reward function, we have the goal function, and it can be expressed in terms of the click probability, the conversion rate, the value per conversion, the cost per click. So why not just forecast this for the next time step and just do the argmax, right? Just greedily take the best bid. So, okay, let's assume that the forecast for this bid, the forecasts are like that. For other bid, the forecasts are like that. And then we can just choose the best bid greedily. So what's the problem with this approach? I mean, this is not a bad approach. We also use this method in our algorithms, but there are some problems with this method. And these are that typically, you do not have enough data about different beats. And this is for several reasons. For instance, when a human runs a campaign, typically people do not have time to change the beats too often. So they will just stick to one beat. Maybe they will change this beat once in a month. So you will have very little data about your X variable and how it impacts other variables, the Y variables. So that's one problem. When, for instance, Google algorithms are used, and these are used quite often because Google provides free solutions to manage beats on Google Ads, then Google does not provide those beats at all, because probably to prevent reverse engineering, right? So you do not have the X variable at all. So you can't fit a model effectively. And then if you only test your models on historical data, you're not prepared on what's to come, right? You only stick to what was in the past, but this is a highly competitive environment. It changes in time, so you have to actually adapt over time. You have to have some exploration, active exploration, online learning in your method, and this is the way to go. And also, this brings us to the point that to test such algorithms that do sequential decision-making, you need a way to test them. The historical data is not enough. Typically, it's not enough. And this is why you need simulators to do it. For instance, in reinforcement learning, when you have an agent playing a game, this is obvious, right? But for such business problems, it's not that obvious, but this is the right practice. Okay, so let's move on to the simulator. Okay, this might scare you, but this is the simulator that we actually created for emulating this Google Ads system. And you can recognize already that, yeah, we have the beats, so this is our policy. We have some competition. We have the VCRE auction. We have the positions, cost per clicks, click probability, clicks, searches, which is equivalent to auctions. Then we have the conversion rate, conversions, value per conversion. And finally, we can calculate the rewards from that. So we have a simulator that emulates the entirety of Google Ads, and therefore we can just plug in some priors to the simulator, because this simulator uses probability distributions to generate as many scenarios as we want. So the only thing that you need to do is to give another seed to the simulator, and you get a completely new scenario that is equivalent in distribution to reality, but the patterns are different. The actual patterns are different. So the actual numbers are different, maybe. This is the better word. So you can test your algorithm against many, many scenarios. Okay, so just to give you a glimpse, these are priors for our simulator. So this is the data for a real campaign. You do not have to understand what's here, but I will just give you some hints. So this is for instance, the maximal click probability that you can expect throughout a year. This is 1 year. So you can see that there is some seasonal effects. For instance, this is January. January is better. For here, you've got the conversion rate. So you can also see that there's a season where the conversion rate is very high. And there is also some weekly patterns. So there are days which are just better than other days. And there are many effects that we can put by putting the right priors into the simulator. And we generated several scenarios based on different types of campaigns. So for instance, for a spa hotel, for instance, for flight tickets selling, small courses selling, software plans, and so on and so on. So we have actually 9 scenarios that we test our algorithms against. Okay, so another very important thing about simulators is that you can, let's say, cheat a bit, because you know the objective reality that's inside the simulator. You know the priors. So what you can actually do, you can calculate the optimal policy. So because you know what are the priors, you know what are the expected values for every bid, you know what are the bids of the competitors, you can actually, in every time step, calculate the optimal bid and the optimal reward that you can get. And this is very useful because normally, if you compare algorithms, you can see you get a number for one algorithm, you get another number for other algorithm, but you don't know how good it is objectively. And in a simulator, you can say it, because 100% is the optimal. If you're at 50%, you know the gap is 50%, right? And so you know how far you are from the best possible solution. So this is a very good benchmark. Okay, let's move on. Okay, that's an idea that you could come up with, that having an optimal policy, you could actually try to teach a neural network to emulate the optimal behavior. But this is a good idea, but one problem with that is you can highly overfit to the scenarios that you have in the simulator. So we haven't tested that yet, but we plan to. Okay, so the scheme that we were using for every algorithm to tune it and test it is given here. So just to briefly say it, we have those 9 scenarios. We have 3 repeats for every scenario. So we give 3 different seeds. And this is a single run of hyperopt. Then we test new parameters. We go to the next iteration. And this way, after 20, 40 iterations, we have tuned parameters. And this we can do for many sets of parameters if needed. And then we do evaluation where we increase the number of repeats from 3 to 9, and this gives us the final evaluation of a result of efficiency of a given policy algorithm. Okay, so just to summarize the benefits of having a simulators before going to the algorithms themselves. So you can really properly test reinforcement learning algorithms with such simulators. Even if you do not have that much data, you can actually figure out what are the right priors, so you can then generate synthetic data with the simulator. So this is very helpful to test your algorithm against different scenarios, and then you mitigate risks before you put your algorithm into production. So, but there are costs, of course. Unfortunately, yeah, you need to have some mathematical knowledge to come up with the right model behind the simulator. The coding of it is pretty costly, unfortunately, and takes quite a lot of time. And then, well, yeah, transforming data into priors is not always absolutely straightforward, and these simulations can take quite some time, so then you pay for the computers, for the computing power, and this is another cost that you have to deal with. Okay, so now to the algorithms. Okay, so yeah, that's the first time I actually show that, but this is more generic than I need for this presentation, but I would like to give you some message here. So this is something I call complexity arrow, and it goes from very complex models with many, many parameters and no expert knowledge involved. And at the bottom, you've got simpler models with few parameters and with much more expert knowledge. So, and you can say, for any algorithm, you can say where it is in this arrow. So for instance, we start with artificial neural networks which have a lot of parameters, and of course they can fit to almost anything because they have so many degrees of freedom that it's obvious that they can fit to it. The only problem is how to do it, right? But but the point is that not often you have enough data to train a neural network. So you need some expert knowledge. And even a convolutional neural network already has some expert knowledge because the structure of the network has this, elicits the figuring out of features of the object that you have, for instance, on an image, right? So there is some expert knowledge in the construction of the network. Then you've got the typical machine learning stuff, models, and finally you have curve of families with certain properties. So if you know something about reality, you can tell it to the model, right? So if you know that some relation is increasing, some relation has certain properties that then you can just choose a proper family of curves and feed it to data. So this way, the model can learn on much, much less data. And this is very useful, and this is what we use a lot in our production systems. So also might be interesting for you that I don't know if you ever thought of it, but even the law of gravity has a tunable parameter. There's only one parameter, but there's a lot of knowledge about reality in it, but still it has one parameter. So let's go further. Yeah, so the main message on this slide is that really using the expert knowledge is pretty important, and in production you will typically end up with using at least some expert knowledge. And most often than not, you will get much better results doing that. Okay, so now the structure of the algorithm. So the algorithms have to store their beliefs about reality. So what's the reward for every bit that they choose, right? So there are several models that you can use for that. And the first one is independent beliefs. So this is just an array of numbers. Every number is the, let's say, average reward that you can expect for a given bid. Right, so that's a very simple belief. And here are the formulas for the Bayesian updating for the independent beliefs. And the important part here is that in the Bayesian setting, all the parameters are interpretable. So here you have the precision of your current belief, and here you have the precision of your measurement. And this will prove important later. And this is just a weighted average, if you look at it properly. Okay, and here we have a formula from other community, computer science community. If you put here 1 over n is just the frequentist approach, it's just the normal average. And if you put a step size rule here, then you can have different behaviors, different convergence properties, but you have to remember that then you just do some engineering stuff, and it might work well, but you don't understand what's this parameter for, right? It doesn't have its explanation in reality. And here you have it. So this is the power of Bayesian approach. Okay, correlated belief, it's just it assumes that there are relations between the beats that are close to each other and the beats that are far from each other are not related. And the Bayesian updating for the correlated beliefs just updates the covariance matrix recursively and learns what are the relations between the rewards for different beats. So that's just the only difference. Then there's the hierarchical belief, and yeah, so that's a different structure. So for instance, this is a very natural structure for logistics, where you have a country, you have regions, sub-regions, and so on. And Professor Powell has a lot of success of gathering information in this form, but actually I give it only for completeness, but it didn't work for us. Okay, and then we have models from other families. So this is Gaussian process. So, well, I think uncertainty is absolutely not visible here, unfortunately. But there should be. So yeah, Gaussian process is kind of similar to the correlated beliefs, but the difference is that the correlated beliefs learn the covariance matrix from data recursively, but the Gaussian process assumes the covariance matrix in a form of a kernel. So that's the main difference, and but in idea they are pretty similar. And then we have parametric beliefs. So we can also, if we have some knowledge about the structure of the rewards, for instance, that they first grow with the beat, then they go down, or we have some knowledge about the structure of the rewards. For instance, here we have, because we know that the conversion rate affects the reward, the click probability affects the reward, so we can model all those with parametric models, simpler models, and we can have the belief that already contains this knowledge that we have as humans, and then this is much easier to feed to real data. So some models that we use in our production system, I do not give all the details, obviously, but yeah, so you can see here that, for instance, for the click probability, we use a curve that's a kind of a sigmoid. I mean, this is a transformation of the sigmoid function, because you can expect that if you give a very low bid, then you will not get clicks. Then there is one point where when you get above the organic results, and you will get some clicks, and then when you get to the first position, it levels out, and you get always the same amount of clicks. So sigmoid function is a nice choice, but we found that a modification of it is even better. For cost per click, you know that because it's the second price auction, so as a human, you know that the cost per click will always be smaller than the bid, right? And typically, it's smaller the farther you are, the bigger the bid. The farther it is from the line of y equals x. Yeah, so you can see that we could feed even the curve to this kind of data. So this is from a campaign managed by a human. So there was one beat all the time throughout a year, and this model was able to do a reasonable guess what's the relation between the beat and CPC, even though, yeah, seemingly you wouldn't be able to feed anything to that, right? So this is the power of parametric models. Okay, so going to the algorithms, so just to give you an idea of the three algorithms solving the multi-armed bandit problem, we have the upper confidence bound. So this, well, maybe one information here. All these algorithms have this mu here, which is the estimate of the reward. So this is the exploitation part. The knowledge that you already have about the rewards, you want to use it, right? So you want to include it in the argmax. But you also want to explore. So this is the part here, and this is the part here, and this is the part here for exploration. And all these algorithms, they differ in how they explore the beats that they haven't explored enough in the past. So this is a pretty engineering approach, that you have the number of time steps that passed and the number of time steps that you tested a given bead. So this is just pure engineering. Here, you already look what is the expected improvement of your reward when you test a given bid. And the difference between knowledge gradient, which might seem pretty similar to expected improvement, is that knowledge gradient actually models more carefully what happens in the next time step. So I just give you an idea. I will not be explaining the formulas exactly, but I will just give you an idea that it takes into account the Bayesian updating that's done, and it calculates the expected reward that you can have from testing this bid. And then it assumes that you would be using this bid for eternity and compares that to the current reward that you get. So it balances what you can get immediately and what you can get from testing another option. And again, the difference between expected improvement and knowledge gradient is that knowledge gradient more carefully models the next time step. Okay, so I think I have not much time, so just to give you an idea of our contribution to those algorithms. So we use independent beliefs. So this is one of our models, and on a small sample of beats. So for instance, we have beats from 0 to 20, but we do not consider them every, for instance, grosh, but we take a sample of like 20 or 30 beats for the computational complexity being lower and for the learning to be more efficient. Then we use independent KG to obtain a vector of value of knowledge. So here you can see that the green one is, the orange, red, this is the value of knowledge, and finally the green is the objective function which balances the expected reward and the value of knowledge. And what we then do, we interpolate those values, objective functions, with a Gaussian process. And why we do that? To also be able to choose not from only this discrete set, but also the points in between. And sometimes Gaussian process can figure out that the best bit to choose is somewhere in between the sample that we have. And you will see that it proves pretty useful. I will skip that. We also tested the correlated belief with this interpolated KG. I will also not go into detail, but you can see maybe just one thing. You can see the comparison that the independent belief actually tests one point and updates the belief only about this one point, and correlated belief also updates the belief about the rewards of neighboring points. Okay, and a couple of other improvements. What we also did, and this is the power of interpretability of the parameters of your models. So what I said is that this is, in the updating formulas, you've got the precision of the measurement. So if you know what it is in reality, you can try to have a model, to create a model to actually estimate it from the data. If you have a step size rule, you don't know what it is in the data, but if you have uncertainty of your measurement, then you know. So we could use the maximum likelihood estimator to actually feed the uncertainty of the measurement. And you can see that it converges very nicely. It's very noisy at the very beginning, so we just start with using some initial value, and then we use the MLE value of the observation noise. Then we can add forgetting, because we have interpretable formulas, so we know that we can just forget a bit of the precision that we already gathered throughout the experimentation that we did. Right, so there is a natural way where to put the forgetting factor. We just remove a bit of the precision of our estimates. Then it's quite important to use the information that you have from the data. So typically in theoretical approach, people use uninformative priors, so they do not have any information included, but it's much better to actually, if you have the data, to guess the right priors. And it helps the model a lot. And of course, Tuning is very important. Professor Paul, if you ever meet him, he will tell you that knowledge gradient, you just don't have to tune it, but yes, you can. I mean, you have to. You really have to, and we struggle with it quite a lot. Okay, so the fun part, a colorful table with results. So first of all, there's the knowledge gradient, and what's here is the percentage of the optimal result, the optimal policy result. And here you have the 9 scenarios that we have in the simulator and the percentage for compared to optimal for those scenarios and the average score here. Right, so the knowledge gradient comes first. Then Gaussian process plus expected improvement is just a bit better, so probably with better tuning, they could be in reverse. They are very similar, and these are out-of-the-box algorithms. Then we have UCB, which is a bit better. It's already 47%. But then we have the Gaussian process belief and interpolated KG, and the jump is really significant. It's 20% point. Then we have the correlated belief and interpolated KG, and it's another 2.5% better. Then we have a first parametric model. So this is a, yes, kind of a code. Yeah, so this is a this hides a certain parametric model. So there are models used that I already showed on the slides, and there are also other models that we use. So this model bases its efficiency on the parametric models to model the click probability, dependency between the beat and the click probability, the beat and cost per click, and so on. And it just uses very naive way of exploring. This is excitation, so it just adds random noise to explore a bit of the neighborhood of the greedy choice. Okay, then finally we have the independent belief plus interpolated KG, and it's on par with the parametric model. So this is, so you have to remember that this is a generic model without any structure in the belief, right? And it's on par with models that use the expert knowledge about the problem. But finally, there is another parametric model that we use with some hidden sauce that we do not disclose at the moment. And this one is the best. Okay, just to show you, there are some other results of other algorithms that we tested, and there are many more. I couldn't fit it here. Okay, just very quickly a summary. So I think knowledge gradient definitely deserves a place, a spot in the core of reinforcement learning algorithms. It should be covered in books like Reinforcement Learning by Sutton and Bartow. I think this is this algorithm is on par among adaptive learning algorithms, and it allows you to learn really fast on interacting with reality and on pretty small data. Moreover, all the parameters in the model are interpretable. So that gives you a lot of room for improvement, because if you understand, you have some intuitions about the parameters, you can change the model, you can apply other techniques to the model and bundle it with other methods, so that you saw that this can be very beneficial. Then, yeah, another message that it's important to understand the interior of the algorithms that you're using, because then you can do sometimes even little tweaks, and they will give you a huge boost in production, right? So this is a pretty important practical advice. And in the presence of little data, using mathematical models and human knowledge will get you very far compared to very generic algorithms. Of course, neural networks are extremely useful, but if you have lots and lots of data and you do not have to adapt to changing reality, right? If you don't know how the reality will be changing and you have to be prepared for the change, then you need adaptive learning algorithms, active learning algorithms like, for instance, knowledge gradient. Okay, just future work. So we work also on multi-dimensional optimization, where we have many keywords and we choose a set of beats for the entire set of keywords under a budget constraint, because a budget constraint is over an entire campaign. And we also aim to obtain a stable solution combining the parametric models and knowledge gradient. And we had some success in this direction, but still these algorithms are not as reliable as we would like to, so they perform well on some scenarios and badly on others. Okay, that's it. Thank you very much.